Hello again, everyone, and welcome to the next lesson in our Cosmic Adventure lecture series. My name is Dr. Valerie Rapson, Assistant Professor of Physics and Astronomy at SUNY Oneonta and past Director of the Dudley Observatory. Today we're going to talk about a really interesting topic, magnetars and fast radio bursts. So fast radio bursts, or FRBs as we're going to call them, these are bright flashes of light that we are picking up at radio wavelengths that astronomers are having a really difficult time explaining where they came from. We're starting to see more and more of these bright flashes, but we're not really sure what in outer space is causing them. It could be these mysterious stars we call magnetars. So to start with this topic today, I'm going to do a little introduction to radio astronomy, talk about how that works and how we actually make our observations of fast radio bursts. Then we'll get into what these bursts are, what have we discovered so far, and what are some information, bits of information that we can use as clues to figure out where they come from. And then we'll finish up by talking about magnetars and other possible sources for the fast radio bursts. We begin our lesson today with a quick introduction to radio astronomy. Radio astronomers utilize large radio antenna or big radio dishes, very similar to the ones you have on top of your house that pick up the cable signal, or the big dishes you see downtown dispersing the TV signals. Except the astronomers use these dishes to point at the sky and pick up radio signals from outer space. Now, all sorts of different things in space can emit radio signals. Planets, stars, galaxies, they all have different mechanisms that can allow them to emit different radio signals that we can pick up here on Earth. The key thing to understand about radio astronomy is that when we talk about picking up radio signals from space, we're not talking about picking up sound. Radio signals are really just a form of long wavelength, low frequency, low energy light waves. So picking up a radio signal from space really means we are collecting radio frequencies of light with our dish or our telescope. We're not listening for signals in space, we are actually collecting light. You can see on the bottom of the slide here, this is our electromagnetic spectrum, all of the different kinds of light. Our eyes are only sensitive to the visible range, this very small range or colors of light between ultraviolet and infrared. And the radio waves are over here. These are the light waves that we're picking up from space. The wavelengths of light that we associate with the radio range are anywhere from as small or as short as 1 millimeter all the way out to 10 meters or longer. So this is generally longer wavelength, lower frequency, lower energy light waves. To collect up these light waves, we said we need these big radio dishes. So how do they work? Well, the radio dishes, they don't need a mirror like a standard telescope. The dish actually acts as a mirror. The light comes in from outer space, bounces off of the main radio dish here. There is a secondary reflector up here where the light bounces off the dish, hits that secondary reflector, and that sends the light down the center of the dish, usually through a feed horn, and then down through the rest of the system here where there's an antenna, a tuner, an amplifier, and then ultimately a computer reads the signal and displays the information for us either in numeric and data form or in picture form if we are trying to create an image of what we are seeing in outer space. Now, radio signals from outer space are very weak compared to the types of radio signals that we are, sending with our TV and our cell phone and all of that. Signals from space are generally 1 billion times less powerful than the radio signals that are sent and received by our cell phones. So the radio dishes and the accompanying equipment has to be incredibly sensitive. You might notice if you've ever looked at where radio dishes exist on Earth, they are in radio quiet zones out in the middle of nowhere because these dishes are designed to be very sensitive to pick up these low energy signals from space. utilizing a microwave or a cell phone nearby would completely overpower the electronics in these telescopes. We have to be very careful about making sure we are observing things in space and not things on the ground. Now, these radio dishes on their own actually reflect a whole range of frequencies or wavelengths of light. But once the light bounces off the main dish and ultimately goes through the feed horn and into the antenna and receiver, it's the receiver and the feed horn together that define what frequency range we are actually going to study. In a lot of radio dishes, the feed horn has to be the same size as the wavelength of light that you're looking at. And if our radio wavelength of light is 10 meters or more, that means we have to have a really large feed horn to capture that frequency of light or that wavelength of light. That means the dish not only has to be large to be able to reflect that wavelength of light, but also to have that feed horn at the center that can collect up that wavelength of light as well. As you will see when I show you some more radio dishes later, they are all really, really large. They're tens to hundreds of feet wide, most of these dishes. Now, the size of the dish helps govern what wavelength or frequency of light you're going to be receiving, but it also helps give you a higher resolution image or a higher quality picture. The clarity or resolution of your image is generally governed by the size of your telescope, or in this case, the size of the radio dish, along with the frequency of light that's being observed. You probably know that in general, larger telescopes are better. Bigger telescopes are better. And that's because the bigger my telescope, the better resolution I'm going to get, the more fine details I'm going to be able to see in my image. The same is true in radio astronomy. The bigger the dish, the higher the resolution image. But the resolution is also dependent on the wavelength of light. And since the wavelength of light in radio astronomy is really, really long, the resolution tends to be worse than what we would have with a standard visible light image. Here is an example on the right-hand side. On the bottom, you have a pretty recognizable picture of Jupiter, right? If I showed you Jupiter through a large telescope, you would expect to see something like this. What you're actually looking at is light from the sun, visible wavelengths of light from the sun bouncing off Jupiter, coming back to Earth and reaching your eyes through the telescope. The top image here is a radio image of the planet Jupiter, and it doesn't look anything like the optical image. You can tell that the image in general is a bit more blurry. It is lower resolution, and that's just a natural effect of the type of light we're looking at and the size telescopes that we're using. So the image is almost always going to be more blurry than an optical image. And we also have to remember that when we are observing radio light, we're not seeing the same thing as we would with visible or optical light. When I look at Jupiter with a radio telescope, I'm not seeing light from the sun reflected off the surface of Jupiter. I'm actually seeing a totally different mechanism that is creating this radio frequency light. It's actually electrons that are trapped in the magnetic field of Jupiter that are releasing radio frequencies. And that is what I'm seeing around the outside. So I see kind of this faint glow of the actual planet, and then I see this brighter area around it, which is triggered by electrons that are caught in Jupiter's magnetic field. So the point here is when we look at radio images, they're generally lower resolution, they're more blurry, which ultimately means it's harder to pinpoint exactly what we're looking at, or maybe harder to match a signal with a specific spot in the sky, right? If I get a bright signal, it's hard to tell, which galaxy or which star that signal came from because the images are lower resolution. And also, we're not looking at a star or a planet or a galaxy in the same way as we normally would with an optical telescope. So just keep all of these things in mind as we now transition into discussing these fast radio bursts and the associating phenomenon that might be causing them. All right, so fast radio bursts, what are they? Well, a fast radio burst is exactly what the name sounds like. It is a bright but short flash of radio frequency light that appears to be coming from outer space. So, a fast radio burst, a burst of light that happens over a short period of time that's very bright coming from outer space. These signals tend to last only a few milliseconds. That's shorter than the blink of an eye. So they truly are quickly received signals. They don't last for a long time. They literally are just a blip on our radar, and then they seem to disappear. The light covers, or the signal covers, a broad range of frequencies. Many of them are around 1400 megahertz, but some of the more recent discoveries have been at different frequencies. But note that they're not always at the same frequency. The frequency can span a large range, or we can detect signals at different radio frequencies. There doesn't seem to be a correlation. They also appear sporadically, and many of them don't have a clear origin. So we see FRBs from all different locations in the sky, and they don't all appear to come from a spot where there's a galaxy or a star or something else in the sky. We can't quite yet correlate the exact location of all of these FRBs and find something that they actually originate from. Now, just to emphasize, how powerful these FRBs actually emit more energy in that tiny fraction of a second than our sun does over an entire century. So these truly are fast bursts of a lot of energy light. Let's take a look at some of these discoveries of FRBs and the data that goes along with them. The very first FRB discovered, nicknamed Lorimer Burst FRB 010724, it was discovered in 2007, but it was actually found in archival data from 2001. So the astronomer, last name Lorimer, was taking a look at data from the Parkes Radio Telescope in Australia, coincidentally one of the telescopes that helped receive the live TV feed from Apollo 11. And he was going through old data from 2001, and he noticed a radio signal that nobody had seen before. It's not uncommon for astronomers to find interesting things in old data. The astronomers that originally took the data were probably focused on a different frequency range or looking for something else. And this fast radio burst didn't have anything to do with the science that they were working on, so they probably didn't even notice it. The signal is shown over here in the upper right. So if you look at the little inset of the chart, this is the most easily understood part. You're basically looking at time on this axis and strength of the signal on the y-axis. So you've got some background radio noise here, and then at a certain moment in time, the signal peaks. So you get a bright flash of light, strong amount of radio frequency hitting the telescope, and then it goes back to normal background afterwards. The signal only lasted for 5 milliseconds. It lasted a very, very short period of time. So these truly are fast radio bursts. The chart in the background here, the bigger one, is showing, again, time on the x-axis, but frequency on the y-axis. So these signals span a range of frequencies, and the actual signal is this kind of diagonal dark line here. Notice that the different frequencies, so you've got increasing frequency going upward, different frequencies seem to arrive at the telescope at different times. Now, this is actually a really interesting and useful effect that's going to be very helpful in determining what these FRBs are and how far away they originate. This effect of this time delay in frequency space is something that we call dispersion. And the concept is that lower frequency light, lower energy, lower frequency light, it travels more slowly through the interstellar space, the space between me and the spot where the light originated, because it's constantly bumping into gases and dust and material between me and the source, and the lower energy light is slowed down. The higher frequency, higher energy light can just shine right through very quickly. It's not as bothered by the stuff in the interstellar medium. So the higher frequency light arrives first. The lower frequency light arrives a little bit later, just a fraction of a second later. And that time delay actually gives us a sense of how far away the object is. The longer the time delay, the farther away the original source must be. So by looking at what we call the dispersion or the dispersion measure, this time delay and frequency space, we can actually tell exactly how far away the FRB originated from. So where did this first FRB come from? The one that was discovered in that 2001 archival data. Recall that we don't have the ability to necessarily pinpoint exact locations in the sky of where these sources come from, but we do get the general direction. And the first FRB seemed to come from the general direction of something we call the Small Magellanic Cloud. The Small Magellanic Cloud is a satellite galaxy of our own Milky Way galaxy. So this is a small galaxy that orbits around the Milky Way galaxy, much like the moon orbits around the Earth. You can see a picture of the Small Magellanic Cloud in the upper right-hand corner here. And another larger picture of it that's not so pretty here, with contours showing the concentration of light and a couple of bright pockets within the galaxy there as well. The FRB came not from the middle of this galaxy, but from a region just below it. So somewhere in this vicinity is where the FRB originated. Originally, astronomers thought, well, maybe this is an object within the Small Magellanic Cloud, at least on the edge there. But remember, we can use that dispersion measure to figure out distance. How far away is the source? And using the dispersion measure, they calculated that the source was 3 billion light years away. That's much too far to come from the Small Magellanic Cloud. To give you a sense of scale, our Milky Way from end to end is only 100,000 light years wide. So 3 billion light years away is far beyond the edge of our galaxy. So it didn't come from inside of the cloud. They also took a look with other telescopes and they saw no other light coming from this location. And the signal did not repeat. They only saw the FRB once. It was a quick flash of light, and then it was gone. So all of this is kind of strange, right? They were like, oh, this weird signal. It doesn't seem to correlate with anything else. I really don't know what it is. It would take some time and some more discoveries before they could really start putting the pieces together and try and figure out, exactly what these fast radio bursts are and where they come from. In 2015, astronomers were again going through some archival data, but this time it was data taken by the Green Bank Telescope, a 300-foot dish out in West Virginia. They were looking at some data that was originally taken in 2011, and they picked up another fast radio burst signal. It was very similar to the first signal that was picked up in 2007, but this time the dispersion measure showed that the object was actually about twice as far away. It originated from some source about 6 billion light years away. So now we had two signals that were similar, both that seemed to originate from very, very far away. This signal was also interesting because it was polarized. Polarization means that the light waves are all kind of moving in the same direction. And when you have a polarized light signal, that usually suggests that the source has a very strong magnetic field because that can result in polarized light. So just to kind of help you understand how all of this works, I'm sure at some point in your life you remember taking a magnet, sprinkling some iron filings over it, and the iron filings, because they are magnetic material, they start to trace out the magnetic field lines, and they start to all align in the same direction along the field lines which trace north to south. So when you have a magnetic field present, either around a magnet here on Earth or a magnetic object in outer space, if there are dust grains or particles in space, they will align with the magnetic field, and any light that passes through them will ultimately get polarized. If you have a plasma, like a superheated star basically, you can also have a magnetic field. And in this case, when the magnetic field travels through the plasma, it's not aligning dust grains because it's a plasma, it's a superheated gas. What it does is it aligns the motion of the electrons, and this will then result in polarized light being emitted from the source. So this signal was really interesting because it appeared to be polarized. The first one was not, but this one was. So this is another piece to our puzzle here. 6 billion light years away from a polarized light source. Things really started to get interesting in 2012. That's when FRB 121102 was discovered, and this was detected by the Arecibo radio telescope. You probably recognize the name Arecibo. If you follow astronomy news at all, you know that late last year the Arecibo telescope broke and it's now completely down for the count. It's out of commission now. The cables that were holding the large dish together actually snapped and the dish fell apart. So unfortunately, Arecibo is not going to be used any longer for astronomical purposes. But for a long time, it was the largest radio dish on Earth. It's a 1,000-foot radio dish that's kind of embedded in the Earth there. It's a fascinating telescope, and it provided a lot of great astronomical information about FRBs and a variety of other sources. But this particular FRB, discovered in 2012, was picked up by Arecibo, and this time we kind of had an idea of where it came from. We were able, because we picked it up with such a large radio dish, we had higher resolution, and we could roughly pinpoint where it came from. And it came from this little galaxy right here. So this image is an optical image from the Gemini Observatory. And what you see in the picture here is mostly some stars, and then you've got these yellow blobs. Many of the yellow blobs are actually distant galaxies. And in the center of the white circle where the FRB appeared to originate, there's a faint blob. And that faint blob is actually a very distant galaxy about 3 billion light years away. It's what we call a dwarf galaxy. It's smaller than our Milky Way. This one in particular is about 1/10 the size of the Milky Way. And it appears to be a younger galaxy. We have other data about this galaxy that tells us that there is active star formation happening. So an FRB from a galaxy that is actively forming stars. That's another cool piece to the puzzle here. This source, though, was not just interesting because we could kind of pinpoint where it came from. This signal was also a repeating signal. This FRB was detected not just once, but every 157 days, the source seemed to flare up. And sometimes we would get a bunch of radio bursts over a few hours' time, like in 4 hours, you might get 10 bursts from this source. And sometimes the periodicity was a little bit longer in a sense that it got active every 157 days, but it might remain active for a month or two, sporadically spitting out signals over that month or two, and then getting quiet again, not emitting any signals until the next 157-day cycle. So this was exciting because it's the first time we've ever seen the signal repeat. And if the signal repeats, that also tells us something about the source. It can't be a one-time event necessarily. It can't be, two objects that collide together, somehow emit this burst of light, because it has to happen over and over and over again in space. So having a repeating signal helps give us more clues about what these radio bursts could be. 2018 was a big year for FRBs because a new telescope came online and the number of discovered FRBs doubled. By this time, astronomers had picked up about 15 or 20 signals in the sky. But when the Australian Square Kilometre Array Pathfinder, or ASCAP, set of telescopes turned on, they discovered pretty quickly 20 new fast radio bursts, and they would go on to discover quite a few more as well. ASCAP is shown here, or at least a small set of the telescopes is. It's 36 radio dishes that are each 12 meters in diameter, and they work together as an array of telescopes. And when you combine telescopes together like this, you can do two cool things. You can look at a large portion of the sky. So the dishes have a 30 square degree field of view, which means that we can monitor a big portion of the sky and pick up radio signals potentially more frequently, right? If we're observing more of the sky, we're going to see potentially more of these fast radio bursts. So we get to see more of the sky, and we can also combine the data from these telescopes to get really high resolution images. These radio telescope arrays, what they do is they combine the data so you basically get an image with resolution as if your telescope was as big as the two farthest separated dishes in the array. So without having to build one giant telescope, you get the same effect. And high resolution means that we'll be able to potentially pinpoint exactly where these FRBs are coming from as they're detected with ASCAP. So this was a phenomenal set of telescopes that really helped this area of astronomy. And so at this point, we were up to about 40 total FRBs discovered. And just to note, none of the 20 new FRBs discovered with this telescope at this time were repeating. They were all just one quick flash, one and done type things, no repeaters in this data set. Speaking of being able to pinpoint exactly where the signals came from, that's exactly what astronomers did with a signal that was detected by ASCAP in 2019. You can see the signal data on the right-hand side here. So if you look at the top, we're seeing a chart similar to what we saw before, with time on this axis and essentially energy or flux on the y-axis. So time progresses by, and then all of a sudden you have a quick spike in energy. That's your radio signal, and then we go back to having a low level of background noise. Here is the picture in frequency space. So this is increasing frequency up, and time on this axis again, where for both of these data sets, they have normalized it so that the signal occurs at time equals 0. So this is really change in time from the original time that the source was picked up. So this signal appears to have come from this lovely galaxy over here. We don't have, a really pretty picture like the one that I showed you from the Gemini Observatory, but from using other observatories, namely the VLT, the Very Large Telescope, astronomers were able to get a rough image of the galaxy that we think this source came from. And that's what this colored blob is here. This is what we call a false color image, where in this case, yellow is brighter, light blue is less bright, and then the dark blue is even less bright. And then the white and the blue is just kind of natural black background of outer space, if we could actually see it with our eyes. So the main galaxy is this blob here. This galaxy is surrounded by two other galaxies, so we call this galaxy A. Here's galaxy B, galaxy C. We don't know if these other two galaxies are actually, gravitationally bound or correlated with galaxy A, or if they're just in the same field of view, the same line of sight as this galaxy. But we know that the signal came from, or appeared to at least come from, galaxy A, and there's a small little circle kind of right above my red dot here at the edge of the yellow circle where the FRB seems to have come from. This galaxy, by the way, it doesn't have a fun name. It's just this giant jumble of letters and numbers here. But this galaxy, it's a bit different than the other one that we pinpointed an FRB in. This is an older, less active Milky Way-sized galaxy. So a galaxy that's not actively forming stars, at least not very much. And the galaxy is a similar distance to many of the others, about 3.6 billion light years away. So this again is another partly contradicting piece to the puzzle, where we saw an FRB in a very young, active star-forming galaxy, and now we're seeing an FRB in an older galaxy that doesn't seem to be forming as many stars. So that's not super helpful in trying to figure out, whether star formation or being young or old has anything to do with these fast radio bursts. But the more radio bursts we discover, the closer we are ultimately going to get to the answer of where in the world, or really where in the universe, did they come from. The last telescope that I want to introduce you to is called CHIME. And CHIME very recently has played a huge role in picking up more FRB signals. CHIME stands for the Canadian Hydrogen Intensity Mapping Experiment Radio Telescope. Basically, it is a funny-looking stationary telescope. This is actually a picture of it here. And it's designed to map hydrogen gas in galaxies, both our own galaxy as well as further away galaxies in space. Hydrogen gas is important because that's the main composition of our galaxies, and by studying the gases and how it's distributed, we can learn something about star formation rates and ages and distances to galaxies. So these telescopes are really useful to extragalactic astronomers, trying to help us understand more about the different types of galaxies and how they work. But because this is not just a single round dish, you can see it's like a long metal array here. It's also a stationary telescope, and because it's designed like this, it looks at a huge patch of the sky, and it relies on the rotation of the Earth to point it. We can't point this radio telescope like we point other telescopes to a certain spot in the sky. It can only observe, directly above where the telescope is, essentially. So this telescope is always looking at the same patch of sky over and over and over again, at least for the time period that the Earth is in one location around the sun. So over a few days' time, we're getting data from the same patch of sky. So basically, this is good for looking for FRBs because, one, we have a big field of view. We can see a large amount of the sky at once. And we're also seeing the same patch of sky multiple days in a row, so we can also look for any repeating FRBs without having to, plan an observing run. We're just naturally going to see the same spot in the sky over and over, so we can see if we get any FRBs that constantly repeat on a day or less time scale. So far, CHIME has discovered tens of bursts, and they anticipate to discover hundreds of them if they actually exist. Understanding FRBs is still a new thing, and there seem to be a lot of them out there, but we don't know exactly how many. But this telescope has the ability to really discover a lot of FRBs for us over time, and it just came online a couple of years ago as well. So we have a lot more data coming in the future to take a look at. One of the most important FRBs that CHIME has picked up to date is FRB 180916. It is the closest fast radio burst that we have discovered outside the Milky Way. And this one we've actually been able to pinpoint the source as well, this time with a really pretty picture of the galaxy. So this fast radio burst appears to come from this spiral galaxy shown here in this Gemini image. The green circle shows the precise location of the radio burst. And this galaxy is only 500 million light years away, which in relative terms is a lot closer, right? The other ones were 3 billion light years away. This one's only 500 million light years away. This is another repeating radio burst as well. This one repeats on a much faster time scale than the first one we talked about. This one appears to have a burst over a 4-day period, so it's active for 4 days, sending out sporadic signals, and then it quiets down for about 12 days, and then it starts up again. So the whole cycle is every 16 days, we see a burst for 4 days, and then a quiet period, and then another burst for 4 days, and a quiet period for 12 days, and so on. Now, since this was a very frequently repeating signal, astronomers that use other telescopes that observe different wavelengths of light decided to take a look at this galaxy in this source. Especially since this is a close source, we can easily see this galaxy and potentially the spot where the FRB or the object that the FRB originates from with other telescopes. Unfortunately, when the Chandra X-ray Observatory looked at, they didn't see any high energy signals. They were starting to think that, maybe something like an explosion or a collision was creating these fast radio bursts. And if that was true, we would expect high energy light to be emitted along with this radio frequency light. But the X-ray Observatory didn't pick up any high energy light, which is kind of a bummer. But again, more clues, more pieces to the puzzle. Not seeing something in this case is almost as good as seeing something. It helps us narrow down our ideas a bit more. So in total, we have discovered over 100 fast radio bursts in different parts of the sky. Here in this map, you can see all of these different dots are representing different sources in the northern and southern hemisphere sky. And the different shapes and colors represent the different observatories that have found these FRBs. And even this map is a little bit old. This was the most recent one that I can find. It's from May of 2019, but it doesn't even include all of the 100 FRBs. And we keep discovering even more sources as time goes by. With all these discoveries, now it's time to start putting the puzzle pieces together. What could be creating these fast radio bursts in the sky? So let's switch gears, and start to talk about what these objects could be. Because these FRBs are quick but energetic bursts of light, astronomers think they might have something to do with the end stage of a massive star's life, or the creation of what we call a neutron star. Here is a cartoon version of how a massive star progresses through its life. A massive star, by the way, is one that is at least 8 to 10 times the mass of the sun or larger. As the star progresses through being born in a nebula, existing as a massive star, as it starts to end its life, it will puff up and become a red supergiant, ultimately ending in a massive supernova explosion, where most of the plasma of the star is spit out into the galaxy. And what's left behind is either the core of that massive star, something we call a neutron star, or if the star is big enough and that supernova is powerful enough, the core can actually implode and create a black hole. Let's take a look at the details of the neutron star a little bit more in depth here. A neutron star is a very small and incredibly dense object. A neutron star is about 1.5 to 3 solar masses of material. So think of 3 times the mass of the sun, compacted down into an object that is less than 30 miles wide. Tons of material squished into a tiny spot. Just to try and give you a sense, here is the Earth, and at the tip of that white arrow, you probably can barely see it. That is the size of a neutron star. So imagine 3 times the mass of the sun squished into something 30 miles wide. The density of this material is so high that 1 teaspoon of the material here on Earth would weigh 4 billion tons. Neutron stars are just incredible. Because of this high density material, the neutron star has an interesting interior. The cartoon on the right shows the different layers of a neutron star. On the outside, we think there is an iron and electron crust. So the cores of massive stars, they create a bunch of different elements until they ultimately get to iron. They can't fuse iron, so the iron is left behind. So we think the top layer of a neutron star is maybe about 1 kilometer or so of iron. And then below that, we have a superfluid. Superfluids are really cool stuff. They're basically a fluid that experiences no friction, and it can just flow without feeling any friction. And it also allows electricity to flow without resistance. So basically, you've got free electrons all over the place, and electricity and magnetism can be generated inside the superfluid material. So the rest of the layers here, we've got superfluid neutrons. That's where the neutron star name comes from. And then below that, there's superconducting protons, more superfluid neutrons, and then down at the center, we don't really know what's happening at the very center. Could be all sorts of weird stuff going on down there. But neutron stars are incredibly dense superfluid objects. So how can these neutron stars ultimately create a fast radio burst? Well, originally, astronomers thought that if two neutron stars collided, that collision would create a tremendous amount of energy, ultimately releasing light at all wavelengths and generating a small black hole at the center of the collision. You can see that in the cartoons here. So here's a cartoon of what it might look like if two neutron stars collided. They would then generate a small black hole, and the cartoon on the right shows how the black hole can then rotate and ultimately pulse some material that's outside of the black hole outward, creating a flow of material and energy. And as this material kind of propagated through space, it would bump into other material in the interstellar medium, heating it up and ultimately releasing various forms of light that we could then receive at Earth. The shock waves would generate high energy light like X-rays and gamma rays, and then moving electrons that are inside of this material can also generate the lower frequency radio waves that we would see as the fast radio bursts. These shock waves could be what's generating those bursts. Now, if it truly is two neutron stars colliding, creating the FRBs, we would also see gamma rays and gravitational waves in this process. So far, we have not seen gamma rays or gravitational wave detections associated with most FRBs. Only in a couple circumstances have we seen this. And this also doesn't explain repeating signals, right? If the neutron stars collide, they're going to do it once, and we're never going to see it again. So this might be a good explanation for the non-repeaters, but for those repeating signals, this is maybe not the best explanation. Thinking about those repeating signals, astronomers said, well, maybe we can blame it on these things called pulsars. Pulsars are formed when a neutron star collapses down and starts to spin incredibly rapidly. As the star's core shrinks, conservation of momentum causes it to spin more quickly. And if it starts to spin at a rate of multiple times a second, it then becomes a pulsar. Pulsars have strong magnetic fields because of their fast spin rate. That results in them accelerating electrons and beaming them out their magnetic poles. So if we take a look at the cartoon on the right, here is our fast spinning neutron star surrounded by this big magnetic field. And then these are the magnetic poles where the magnetic fields are open. The electrons that are spinning, that are trapped in those open magnetic field lines, they spit out radio waves, and we can actually see these radio waves here on Earth. This is how we originally discovered pulsars. Pulsars and radio signals from pulsars are not a new thing. They act very much like a lighthouse. So here is a little animation where the pulsar is rotating and the two orange cones are the magnetic poles. And every time the pulsar spins so that that yellow cone points at the screen, points at Earth, we get a flash of radio signals. So we can detect these pulsars with radio telescopes. We know about a whole bunch of them. But are they associated with FRBs? Is there something within the pulsar that could generate a faster, stronger burst of radio frequency light rather than the standard repeating pulses that we constantly get from a regular pulsar. Well, maybe. So if the signal repeats because the pulsar is rotating, that could explain the repeating bursts. The pulsar would also need to wobble a bit or do something that would change how bright the signals are and potentially something that might change their frequency as well. And the tricky thing is, we should be able to see pulsars in gamma rays and X-rays and other types of light. We have observed pulsars and other objects with these other types of telescopes. So when we look at the source of an FRB and we don't see anything with a different telescope, it's hard to use pulsar as that explanation. Unless the pulsar is so far away, it's just too faint in those other wavelengths to observe. So it doesn't completely rule out pulsars for FRBs, but it's not like, oh, definitely that's it. With no real solid explanation for FRBs, astronomers were getting a little bit stumped until they had this big breakthrough in 2020. They detected FRB 200428 with CHIME, and this was the first fast radio burst that we had ever discovered inside of the Milky Way galaxy. Every single other fast radio burst that we saw was in a galaxy or a location outside the Milky Way. This one came from within the constellation Vulpecula, basically a small fox right in the middle of what we call the summer triangle in the sky. So you can actually go outside in the summertime and look towards the direction of the fast radio burst. And this signal came from about 30,000 light years away, which is basically almost the other side of the galaxy compared to us. Here is the signal on the right-hand side, very similar to what we saw before. So this is showing you the signal peak zoomed in, and then here is the signal in frequency, time, space, where the darker color is representing the signal there. And what was really exciting about this is, one, it's in the Milky Way, which means that whatever's causing fast radio bursts are also in our galaxy. They were just as bright and powerful as the extragalactic sources, so it seems to be a similar culprit, whatever it is. And we saw corresponding X-ray emission. So this is great. Now we're seeing the source with multiple types of telescopes, not just with the radio telescopes. The really exciting breakthrough came when we also noticed that this fast radio burst came from exactly the same spot in the sky as a known magnetar. So let me explain to you now what a magnetar is and how it links up with these fast radio bursts. A magnetar is a neutron star that spins a little bit more slowly than a pulsar. So depending on the spin rate of the neutron star, that can govern the property of the neutron star and whether we call it a pulsar or a magnetar. Magnetars rotate only once every few seconds as opposed to multiple times a second. What's really different about magnetars is that they possess an incredibly strong magnetic field. Their magnetic field is 1 trillion times stronger than the magnetic field generated by the Earth and 100 million times stronger than the strongest magnet we've ever developed or found on Earth. So really powerful magnetic fields. To give you a sense of just how strong that is, if you got 600 miles away from a magnetar, the magnetic field would be so strong that it would rip your atoms apart, because your atoms have positive and negative charges, and your atoms would be influenced so much by the magnetic field that they wouldn't be able to stay together. And you literally would magnetically be torn to shreds. Really, really crazy stuff. So magnetars are these bizarre objects. We've only discovered about 30 of them in the Milky Way so far, and we're just beginning to understand, what they are and exactly how they work. How do we get a strong magnetic field inside of these neutron stars? Well, if you ask a physicist, they're going to say, oh, it's just magnetohydrodynamics, no big deal. And you stare at them and you go like, what? What is magnetohydrodynamics? So basically, it's a complicated process that nobody really understands. But I'm going to walk you through the super basics of how we think magnetars get their magnetic field, with the caveat that we don't really understand the dynamo effect inside of Earth or stars or any objects yet. So there's a lot of hand waving going on here. But basically what happens is we know that massive stars have a strong magnetic field. The sun has a magnetic field. We know that there is plasma inside of stars. There's moving charges, so we can generate an electric and magnetic field. So the star, massive star might look something like this with the big field lines around it. Once the star dies, the core, likely where the magnetic field is generated, holds on to that magnetic field. So the star goes supernova, spits its plasma guts into the universe. The core contracts, but the core becomes a superconducting fluid that can hold on to that original magnetic field. So the magnetic field probably stays with the star. And because the star is shrinking down, the core is shrinking down, the material becomes more dense and the magnetic field can actually become a little bit stronger. So the core contracts, it ultimately forms a magnetar. And at the rate when the core has contracted enough so that it spins once every few seconds, something is happening, and this is where the hand waviness comes in, where the heat and the temperature and the energy generation are all just right so that the heat and the rotational energy can get converted into magnetic energy. We don't really know the physics that goes into that part, but something like that must happen inside of this star, creating this tremendously strong magnetic field. The magnetic field doesn't last forever, though. It seems to die down after about 10,000 years, we think, based on modeling and observations we've been able to make. And then the object just becomes a standard boring neutron star. So it's only a magnetar for a short period of time relative to the lifetime of a star. So that's how we think that these stars can have such a strong magnetic field. So how do we get magnetars to create a burst of energy and release a fast radio burst? Well, we think magnetars actually exhibit star quakes. Basically, the same thing as an earthquake, except it's the inside of the star that is shaking and not the surface of a rocky planet. Inside of the magnetar, remember, you have that moving superfluid. And if that fluid starts to vibrate, it can create a synchronous vibration in the crust and actually crack the surface of the magnetar. That's what the cartoon is showing here. You've got your surface of the magnetar and the vibrations, the star quakes can actually crack the surface. When you crack the surface, you totally disrupt the flow of the magnetic field, and that allows some material, some of that fluid or plasma, to follow the magnetic field lines away from the star and actually get released into outer space. Now, just to give you a sense of how powerful these star quakes are, some modeling shows that on a magnetar, a star quake would actually measure magnitude 23 on the Richter scale. That's hundreds of times more powerful than the strongest earthquakes we have ever measured. So these are really, really tremendously powerful fractures on the surface of this star. Once the plasma flies away into outer space, we see something very similar to what we discussed before when we were talking about the merging neutron stars and the black hole pushing material away into space, creating a shock wave. The same kind of thing happens from our magnetar. If you follow the cartoon, here's our magnetar releasing a flare into outer space because of that star quake. The flare pushes forward through the interstellar medium. The flare collides with debris, maybe from a previous flare or just debris that's just already around the star. And that collision heats up the material, and that hot material will release gamma rays and X-rays. And then the electrons, as you see on the bottom, they are going to get caught up in the magnetic field lines. They're going to spiral really quickly, and those added electrons are going to generate an even stronger magnetic field right at the shock front. And that stronger magnetic field is going to ultimately release radio waves. Those twisting electrons, they naturally emit those radio frequencies, and that could be our fast radio burst that we're seeing. So we would get our X-rays from the collision, and our oscillating electrons would create our radio frequencies, our fast radio bursts. So magnetars could do it. They could be creating the bursts that we are seeing in outer space. And because we have a magnetar that correlates with one of the detected bursts within the Milky Way, this seems like a plausible mechanism for this to occur. So to finally answer the question of, do magnetars solve the FRB mystery once and for all? The answer is maybe, right? Not all the puzzle pieces fit together exactly like we would want them to for this to be the only solution. So we have a possible mechanism for a magnetar to create a burst of radio light, and we have seen that correlated signal, so we're pretty sure that it can happen. So this could be one of the possible scenarios. We also know that the strong magnetic field from the magnetar would create a polarized signal. Remember, some of our early on FRBs were polarized light, and we need a strong magnetic field around the source to create that polarized light, so a magnetar would definitely do that. And we also, as we said, some FRBs are coincident with known magnetars in the sky. So if they match together, they are likely the source. But not everything fits. It's hard, again, to explain those repeating FRBs. Pulsars and magnetars are not the same thing. We don't think all pulsars are magnetars. But it's possible that there's a specific type of pulsar that we haven't quite narrowed down yet that does produce FRBs, whereas others don't. We have a lot more work to do in this area to figure that out. Not all FRBs also have the corresponding extra light, right? We said with the one in our Milky Way that we saw X-rays and we saw other types of light from it. But not all of them have that high energy light that we would expect from a magnetar releasing the energy. So we don't have a full solution. I can't answer the question, but I can put all the pieces on the table and we can start to fit them together. And this is basically where we stand at the moment. This is what astronomers know about FRBs. This is how they relate to magnetars. And I believe that as we discover more and more of these fast radio bursts, we'll start to narrow down the scenarios. And maybe just in a few short years, we'll finally have an answer once and for all to the FRB mystery.